Hello everyone, I am so happy to have you here. This is my first YouTube video and I am truly excited to launch this project. My goal with this channel is to produce educational content that explores the most vital frontiers of contemporary thought, such as the philosophy of science, formal logic, and the philosophy of artificial intelligence. Before we begin, I would like to express my sincere gratitude to my instructor at Middle East Technical University, Associate Professor Aziz Fevzi Zambak, for his guidance and contributions that made this video possible as part of our Philosophy of Logic and Mathematics course. Today, we are going to explore the Curry-Howard correspondence, which bridges the gap between the abstract world of logic and the practical world of computation. We will uncover the concepts that define how we understand mathematical truth today. Philosophy is a constant act of questioning, and by examining the intersection of logic and computation, we aren't just learning theorems. We are examining the tools that define intelligence itself. I view this channel as a laboratory where we can generate ideas together. I look forward to deepening this investigation with your support. If you're ready, let's jump into the analysis. Hello everyone. My name is Al-Haz, and I am a second-year student at the Middle East Technical University, Department of Philosophy. Today I would like to talk to you about a profound connection, a bridge that effectively tears down the wall between mathematics, logic, and computer science, unifying them into a single, elegant language, the Curry-Howard correspondence. For many years, the world of proofs, which occupied logicians, and the world of programs, which was built by computer scientists, were treated as if they belonged to two entirely different universes. Logicians focused on what truth is and the provability of mathematical statements, while computer scientists were concerned with the efficiency and computability of algorithms. However, the Curry-Howard correspondence revealed that these two worlds are, in fact, two sides of the same coin. There is a direct correspondence, a structural isomorphism, between the structure of a mathematical proof and the structure of a computer program. But why is this so significant? Because it demonstrates that a mathematical proof is not merely a theoretical construct. Rather, it is, in essence, an executable, testable, and computable program. In this presentation, I will examine the foundations of this correspondence, specifically the elegant notion that proofs are programs and formulas are types, and why this represents a pivotal turning point in our philosophical understanding of mathematics. Let us now look at the core of this correspondence, the principle that proofs are programs. To understand this, we must consider the structural similarity between logical deduction and computation. The most intuitive example of this is the relationship between logical implication and function types. In logic, if we have a proof that A implies B, A implies B, we have a method that transforms a proof of A into a proof of B. In computer science, this is exactly equivalent to a function that takes an input of type A and returns an output of type B. Therefore, the act of proving a theorem is, from a computational perspective, the act of constructing a program that satisfies a specific type. This means that a logical formula is not just a statement of truth, it is a specification for a program. When we write a proof in a system like Coq or Lean, we are actually writing code that is correct by construction. This insight shifts our view of mathematics from a static collection of truths to a dynamic, computable system. Beyond the technical elegance, the Curry-Howard correspondence carries profound philosophical implications. It challenges the traditional view of mathematics as a collection of static, eternal truths that exist independently of our actions. Instead, it aligns closely with the constructivist perspective, suggesting that mathematical objects are entities we create through our constructive activities. If a proof is equivalent to a program, then mathematical truth is fundamentally linked to computational content. This means that to assert a mathematical statement is true is, in a sense, to possess a recipe or a program that can produce that result. Furthermore, this correspondence blurs the boundary between knowing and doing. It suggests that the epistemic status of an intuition, our belief that something is true, is inseparable from our ability to execute or verify that process computationally. By bridging logic and computation, we move toward an ontology of mathematics where the being of a mathematical object is defined by its computable behavior. Ultimately, this shifts our understanding of mathematical proof from an act of persuasion to a rigorous, verifiable act of engineering. To conclude, the Curry-Howard correspondence is far more than a mere curiosity of logic. It is a fundamental pillar of modern formal ontology and computational mathematics. By demonstrating that proofs and programs are essentially the same entities, it has provided the theoretical foundation for advanced systems like dependent type theory, which allow us to write software that is mathematically guaranteed to be correct. When we reflect on the implications of this, we realize that we have moved past the classical dichotomy between abstract reasoning and mechanical computation. We have discovered that the very act of thinking mathematically is isomorphic to the act of constructing a robust executable program. This convergence suggests that mathematical truth is not a static realm waiting to be discovered, but rather an active, constructive process that bridges the gap between human cognition and algorithmic rigor. Looking forward, this correspondence suggests that the boundary between mathematical intuition and algorithmic execution will continue to fade. As we integrate more AI-driven theorem provers and hybrid systems into our research, our very definition of mathematical understanding is evolving. We are moving toward a future where proof is not just a human-readable argument, subject to error and ambiguity, but a rigorous, machine-verified process that stands on the bedrock of computational verification. Ultimately, Curry-Howard teaches us that to understand mathematics is to understand the language of construction itself. It defines a future where our most complex logical inquiries are transformed into verified realities. Thank you for your attention, and I look forward to your questions.